Okay, so chapter 3 in ADS is about two more simulators. One simulator is AC simulation. Other one is the transient. So I just wanted to detail to you what is a AC simulation and what is a transient. So before that, let's make a new workspace, and I'm going to call this as chapter 3 in ADS. Just one second. Chapter 3 in ADS. And okay. And here, as far as technology is concerned, I'm going to attach another PTK. Here it is called IHP silicon germanium PTK. It's over here. lib.dev. Say OK. So I'm going to say OK, and then I'm going to set up the layout technology file immediately, which sets up the resolution. Say create workspace. Okay, so again the resolution is 0.001, but when I do layouts, I'm going to use a 0.05 resolution, right? Okay, so now we have a blank presentation. Now, blank project. Now I just wanted to tell you what is AC simulation. Okay, so in AC simulation, what we do is we linearize all the non-linear components. Like for example, if there is a transistor, or let's say if there is a diode which has a non-linear characteristics. So what the simulator is going to do is it's going to linearize the response or the transfer function of that circuit component to be linear around the bias point. So what does it do? Okay, what it does is that the circuit analysis becomes totally linear. And second thing is that there is no restriction of the supply voltage. So for example, even if you put a supply voltage of, let's say, 3 volts, and if you give a signal which results in an output voltage swing greater than 3 volts, maybe 100 200 volts, it is going to show you output voltage swing of 200 volts, right? Now how is it possible? What is the use of such a simulation? Well, as I told you, it linearizes the response. So if the response is linear for any transfer function, so high gain blocks are going to give you very large voltage swings, and that can exceed even the supply voltage. Now what's the advantage of doing this is, well, this is going to be used for what is known as stability analysis. So you'll be able to do a Bode plot, and you'll be able to establish a phase margin. So this is going to be used mostly in analog circuit designs. So AC simulations are used for that. So now what I'm going to do is I'm going to create a uh, new schematic. Okay, and I will call this as let's say operational amplifier or op amp. Okay, so I'll call this a op amp two stage. So this is going to be two stage op amp, and create it. So you see these devices over here. I want to use an NMOS device, and there is a PMOS device. So first of all, I'm going to make a current mirror. So if you want to know more about op-amp, there is another playlist on analog circuit design which you can refer to for this kind of design. So let's just proceed making a very quickly an op-amp. Okay, so here the 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 width. Okay, so let's make this, let's say, 2 micron, and number of gates, let's say, is 2, and make it 5 micron. Okay, so basically there are two fingers. Each finger is 2.5 microns, and then the gate length is 130 nanometer, and the total width of the device is 5 micrometer. Okay, so once you're done with this, what you're going to do is you have to ground this or you have to connect this, and that you'd use p tab 1. So let me see if there is a p tab 1. So n tab 1, sorry. Okay, so now this tie, okay, would go to, okay, so this well would be connecting here, and the tie would be connecting to the supply. Okay, so of course, you know, if there is off-grid stuff, so you can go to layout preference, or you can go to sorry, options preferences, and don't worry about, okay, over here you can change the grid snap, you can choose pin, and you can choose something like 0625. So that's half the grid which is available. Apply, save as a copy, save as a schematic preference, and say okay. Okay, so don't worry about what this is. Okay, so this is tied to the well, and this is tied to the supply. Right, so this is a one PMOS device. Then I'm going to use another PMOS device, so I'm going to make a copy of it. Then I'm going to mirror this out like this. Right, so now, okay, so this is a 1:1 current mirror, and again more on current mirrors in analog circuit design using ADS. So here I am going to have this device size, let's say I make this as uh, this is 5 microns, so I want to make 50 microns. So let's start with 10, make it 4. I don't want to have warnings, so that's I'm doing in stages. So I want 50. Does it allow me to 50? So no, it doesn't. So how about 20 microns? So don't worry about this. Okay, so each one is 5. So then, so 2, so I can make this as 10, and then this one as 50. Okay, so this is going to be 1:10. Okay, so here again I want to keep this as, so I'll make this as 20 gates. Okay, so this is 2.5 and to 20, that is 50 micron, and this is 2.5 into 2, that is 5 microns. So this is a 1:10 current mirror. Then I am going to take the same device. So now I am going to force certain current. So I'll go to simulation. So I want to go to sources frequency domain and put a current source in here. So let's say I draw a current of let's say 50 microamps. So then the output current would be 5 microamps. Correct? Okay, and then you have a VDD. Let's say this VDD is 2.2 volts. Okay, so this lag is going to force a current of 500 microamps. So I'm going to make copy of 2. So I'm going to make this transistor 2 times here. So I'm just going to copy it. So one is over here. The other one is going to be copy of that. I'll flip it over here. Okay, so this is going to be my gain stage, a differential gain stage, and then I need a load, right? So this is a 20, so I would do half of that. So basically I'll use 25 and 10 fingers. So I'm going to just make an NMOS device here. So I'm going to choose a NMOS device here. Where did it go? Everything. Okay, so I'm going to use a NMOS device here. That's an NMOS device. And this NMOS device is going to be 25 into and 10. So let's go and make this as 10 micron, which it will allow. And then there are 10 fingers. Okay, so there are 10 fingers. So that's the size of 25. Okay, so again 2.5 micron. So okay, so this is one, and then I am going to make a copy of this and mirror it out. So this is a current this is a differential stage with this load, right? So here the substrate tie. Okay, so the substrate is going to be tied not to the ground but to using a P tap. Okay, so this will go to the sub, not the ground. Okay, so I am going to put in a sub contact, right? So here I'm going to repeat that. So this is going to go to sub bank, and whenever you put this exclamation mark, that means it's a global node, right? So these two are global nodes, and here I am going to ground that using this contact, where one side is going to be grounded. Okay, so and other side I will name as sub bank. Okay, so now these two nodes are connected that way. So that's how the substrate is grounded. These two devices, NMOS devices, sit in the substrate directly. Now, if you want information on all this stuff, you can refer to the analog circuit design using ADS playlist. Okay, so now after that, I am going to have twice the size as another gain stage. So I'm just going to copy this one in like this, and this is for systemic offset voltage to be 0. I want to size this to be twice the size of these transistors, right? So this one I can make 50, right? Okay, the issue here is the following. Okay, for now I'm just going to hit OK. So now here what I want to do is I want to keep these two overdrives same. So when the current is halved, then the size has to be doubled, right? So if I make this as 100, so I can make this as 100, and I can use 40 fingers. Similarly, this can be 100. And I'm going to use 40 fingers. Okay, so the overdrive of that is same as this. Then the next thing is I want to make this as 50 and 20 fingers. Okay, so this one is also 50 with 20 fingers. So this one is going to be, let me see what has happened. Hmm. So let's undo this. Let's keep it. Okay, let's undo this. This is 25, this is 25, this is 50, and this is 50. Now this one is twice of this one, so this is 50. And this would be the output, which will be given as a input to this common source. And then I want to make this one as 100. So I'll make 100 with 40 fingers. So this is going to be 100 with 40 fingers. With 40 fingers. Okay, so this is a 1:20 ratio. That's fine. And then I'm going to repeat this. So to repeat it, sorry, to repeat this, so now this would force the same current. This would force the same current in the output transistor, right? And this is going to be drawn from the same current mirror. So basically it is going to do, so this is 50, so this is 500, sorry, 1 milliamps. So if it is 25, then there will be 500 microamps in this, 500 microamps in this, and the size of this one is 100 and the size of this one is 50. So the reason for doing this overdrive balancing is that I want to make sure that the systemic offset voltage is 0. Okay, so this is the design for an op amp, and I am going to have inverting and non-inverting inputs over here. So if this node is low, then this node is pulled up and this node is pulled down. So if this is low, this is low. So this is going to be a non-inverting input. Okay, so I'm going to go to sources, frequency domain, okay, and VAC. So I'll put here a VAC, and I want a VAC of 0.5, okay, and I want to give it a certain bias. Okay, so basically that bias is decided by, okay, VDD minus V overdrive is going to be that, and then minus V overdrive again, and plus VT is 0.4, 0.2, 0.2. That is going to be 0.8. So 0.8 from here is going to be 1.4. So I can give it easily as, because the common mode voltage range is large, right? So I can give it a DC value. So there is a DC value over here. So I can give it a DC value of, let's say, 1 volt, and I will display this, right? So this is going to be a non-inverting input, and then I am going to have an inverting input, so I'm going to make a copy of this over here, and that will be driving this terminal, but then it's going to be 180-degree out of phase, so that's going to be 180-degree out of phase. Okay, so now having done that, this is going to be my output. Okay, so in the output I am going to terminate, or rather I'm going to directly put a VO here, so name this as VO. Okay, and so VO in dB will be same as so VO in dB would be the gain, and this is gain because the input voltage is 1 volt across, right? So 0.5 is 180-degree out of phase. Okay, so we are ready with the circuit for simulation. We need a include file, so let's look for include file here. So this is a process include file, and then I am going to do here uh, um, AC simulation, right? So simulation AC. Okay, so in AC simulation I'm going to sweep, logarithmic sweep. So I'm going to go from 1 kilohertz to, let's say, 10 gigahertz, and I want to give it a log, and I want to do 80 points per decade. Okay, and if you want to adjust the display, you can, instead of start stop step, you can say, okay, so start stop remains, and then you can say number of points per decade, so that's 80. So you are going to do AC simulation on this, and I'm going to plot VO and see what happens. Okay, now one thing is going to happen is that it's going to be unstable, so let's see what it does. Okay, so I'm going to plot VO in dB. Okay, and then I am going to put a log scale on the x-axis. Okay, so this gives me a gain of 34. Actually, this dB VO by VI 20 log of, right? So this is not doing a 20 log, is it? So what I can do is I can write a formula for that. Let's see if this is correct. So gain would be equal to 20 into log 10 of VO. Okay, and is the gain a complex number? Let's see if I plot it. Go to equations. So it is a complex number, that's why it is doing that. So I would say magnitude of VO. Okay, now I'll go back to equations and plot gain. Okay, it comes out to be the same. So I'll put it in log scale on y-axis. Okay, so now we have a gain which is 34 dB. So writing the formula also gives you the same gain, doesn't matter, right? And the phase is going to be the phase of S21, phase of this VO. So that's the phase. Okay, so now you see that when the gain becomes 0, how much is the phase? So I'm going to use this one, and I would see when the gain becomes 0, so somewhere over here, the phase is minus 164. So it has rolled almost 180 degrees. So you still have a certain margin, but that margin is not good enough, isn't it? So this one I can delete now. Okay, so the margin is not good enough. So I have to do a lead compensation on this. So this is a Bode plot, right? I can also split this. So if you split it, that marker won't work. It does, but it does mess up the unit. So let's say VO of, so that's not degree, that's dB. Okay, so the gain becomes negative over here, and then that's the margin. So this is referred to as the magnitude plot, and this is referred to as the phase plot, right? Now what I want to do is I want to have certain margin here. So I will do a lead compensation here. So I will insert here a resistor and a capacitor, first an ideal one, right? So I can put here something like 1K. Okay, so I can put here 1 kilo ohm. Okay, F5. Then I'm going to put here 1 picofarad capacitor, roughly. Okay, so I'm going to just drag it out. Okay, F5. Okay, and this is not connected, so don't confuse that this is connected. Okay, so this is a RC compensation, and I am assuming that I have stabilized this, but still I'm going to put a tune on this one, and I'm going to put tune on this resistor and this capacitor. So now I'm going to look at this margin. So the gain becomes 0 at the same spot, and we have a slightly improved margin. So here I need to relax this resistor value and capacitor. Okay, so now let's see the zero crossing. Okay, so now I have rolled over 76 degrees, and I have almost 104 more degrees to go. So now I have a 104 degrees margin, right? So this is going to be called the unity gain bandwidth. So unity gain bandwidth is around 4.57 gigahertz, right? And then I want to look at the corner frequency. So corner frequency is when the gain drops by 3 dB. So if it is 34.8, then I am expecting 31.8. So over here, so 12 megahertz is the TDB point. Okay, so this op amp is usable up to 12 megahertz. So that's the first corner frequency. And here what you see here is you have put in a 0 between the dominant pole and the second pole. So that's why this phase, which has rolled by 90, becomes okay. Basically phase rolls back. Okay, so having done this, I have explained you. So I'm going to update this, close this, and what I want to do is I want to replace this by a resistor here from the library. So if I go to the library and if I look for a resistance, so this is high and this one is low resistance. So let's see what that is. So if I double click this, So I want 540. Okay, so let's say the width is 1 micron and the length I cannot change, so let's say this one is going to be 500 ohm. So it's going to cry? No. So the length is 72 micron. Now if I want, I'll be able to do a bend. Okay, so what is that band? So what I can do is I can put two resistors. So what I want is 54k, 0.540 ohm, right? So here I'm going to make it a 540 ohm. Okay, now there is hardly any current in it. So if you want, you can make it thinner, 0.6 micro. So 48 micro is the length. Okay, so this is a 540 here. So I'm going to replace this with this 540. And then I'm going to replace this capacitor with 0.66. So if I go to the main capacitor, okay, I'm going to use a CMIM and I want 0.66. So right now, so I want 0.66 pico. Width and length are not changeable. So I want 0.66 pico, 20 by 20 micron. So that's the capacitor. And I'm going to resimulate to see if it looks okay. Sorry. So I'm going to save it to simulate it. Okay, so this almost is the same performance, isn't it? Okay, so I have op amp. So what I want to do is I can do some diagnostic on this op amp. Okay, so this is a linear simulation or AC simulation here, where the components are linearized, supply restrictions are not there. And if I was to plot the output voltage, so let's go to the, okay, so if I plot VO in time domain, oh, this is not going to show up. Hang on. So how would I go about doing that? Okay, let's not worry about that. Okay, so now this is what an op amp is doing here. 30, the DC gain is around 34.8. Okay, this is not great, but if you want to improve this, you can use telescopic cascode or a wide swing cascode current mirror. You can use a cascode output stage. You can use a cascode stage over here to establish the load for these two transistors, right? So that's there. One quick way of increasing gain can be if I lower the current, the gain can go up. Okay, so not, the gain hasn't gone up. The margins on the other hand have changed. Okay, so I don't know why this is not working, but let's de-annotate DC, because if you lower the current, the output resistance goes up and the gain is supposed to go up. So if I do simulate annotate DC, or I can do annotate DC from here, currents. So this is drawing 500, this is drawing 800. Should also draw 500, isn't it? Because the two transistors are alike, isn't it? But then this voltage is not the same. Okay, so it means that the output resistance is not good. That's why it's not good. Okay, so another thing I can do is I can double this to 260 if this allows me, and I can make this 200, and this one is okay, and here also I can make it 260, and then I can make this as 100. So the size has remained the same. Okay, here why am I using 10? I should have used 20 to start with, right? This is the offset voltage here, right? So now this is 20 and then this is 100. Okay, and then I can make this one as 260 nano and this one as 50. And this is 50, and this is going to be 26. And this one also I'm going to scale up to 100 and 260. And this is 100 and 260. Okay, so I'm going to expect some improvement in gain because I've changed the lengths of the device. So I have changed the RDS. Okay, very slight improvement here. 45.9. And over here 45.9, 44, 43, 42.9. 42.9. Roughly here. Corner frequency. And here the phase has rolled over, so I would put here unwrap. So unwrap. Okay, so the same curve is back. So here I'm going to see the zero crossing. So this is M1. So the zero crossing is over here. So 102. So I have a 78 degrees margin here. The gain of the op-amp is almost 46, right? Okay, so by changing the length or by reducing the current, you should be able to do this. but for some reason it's not living. Okay, let's see. This should have common mode input. Common mode voltage range is very large, right? So this would not do anything, right? So this is AC simulation. So I hope you understand what is the purpose of AC simulation. The purpose of AC simulation is to determine the stability of circuits which are open loop here or with the feedback loop. So I'm going to make this into what you call a symbol for this. Okay, so to make a symbol, all you have to do is, so I'm going to just save as or save a copy of this. Okay, so this is the performance. So I'm going to save a copy of this. So I'm going to say copy cell, and I'm going to put here COMP. So this is a component, right? And then here I can make a sub circuit out of this. So this is something which is you will use a lot. So I'm going to delete everything from here, including this one. And here I'm going to add pins. So what are sub circuits? Sub circuits are nothing but the lower level hierarchy circuits with pins, correct? So the pins are VDD. So this is a VDD. This is IREF. So this is IREF, and you have to pull down. So I'll say DN for pull down. And how much current am I going to pull down? 25 micrometer. So that's how I label this pin. Then I have got NINV, non-inverting input, which is going to be this one. And then I have a INV, which is the inverting input, which is going to be this one. Sorry about that. Just bear with me. Okay. Okay, non-inverting inverting input, and then there is output. Okay, for sub-bank we don't need any pin because this is a global variable. So this will be VO. Okay, so now we have connected the pins. We can save it, close it, and then we can make a new symbol for this cell. Okay, say okay. And here I want this to look like an op amp, not a rectangular graph. So I am going to use this as my symbol, and I can put here VDD, and I can put here inverting and non-inverting input. So I'll just mirror it out. Okay, so VDD I can take up, this down, and this up. So this is inverting and non-inverting input, and then I can put the output here. So this is going to be output, and then I am going to put here the current reference here. So I'm going to move this one over here. So I'll connect it over here. So that's the symbol for the op amp which I'm going to use. So this is how you do a symbol for a cell. Okay, so then you can do a test bench. So I can go here and say new schematic, and I would say test slew. So I want to test the slew rate. Okay, create a schematic, and here I am going to do a time domain or a transient simulation. Okay, so this is not a AC simulation, this is a non-linear simulation. So here the components are not linearized. So I'll put a AC component in here. Okay, and I can move the text around Fine. So here I want to draw a current out. So first of all, I also need this one. So this one, the top node is called sub bank. Okay, so that sub bank is connected properly. Then I can do a supply here. So I go to sources frequency domain, and I'm going to put a 2.2 volt supply here. Okay, and then I want to draw some current out of this. Okay, I forgot to take out ground, is it? Okay, I have given grounds here. I can add another pin. Okay, so let's delete this. Okay, and let's put another pin here. So I'll call this pin 6 as ground. Okay, and let me connect. Okay, so that's the ground pin, and in the symbol also I have to add this pin. So I have to introduce a 6th pin. So just copy this. So that's pin number 6, and I have to call this pin as ground. Same name if you it's case sensitive. Okay, and I can edit this text to be a okay. Then I am going to rotate this. Okay, and place it somewhere here, ground over here, and I can just complete the connection like this. So this is just a okay. So if it's off the grid, you can temporarily switch off the snap, drag it, and then put back the snap on. Okay, so that's my ground terminal. And here, when I do the test, okay, this is updated. So let me bring this back again. Okay, so this is the ground terminal. And then I need to put here a current source or a current sink. So go to sources frequency domain and put a IDC here, which is 25 microamperes, as the pin name says, 25 microamperes. Okay, so now if you want to do a transient simulation on this, you have to make sure that there is a right DC value. Okay, so 2.2 volts, right? So the gain is 40. Okay, so gain is 40 dB. So I will take this in millivolts. So I'll go to pulse, and the frequency I'm going to put here is going to be because if you see what's the response of a op amp, it goes up to 3.6 megahertz. So I'm going to use somewhere at 1 megahertz, right? So if I want to use this at 1 megahertz, okay, 1 megahertz means a time period of 1 microsecond. 1 megahertz would mean a time period of microseconds, isn't it? So here I am going to have a 0.5 microseconds, so 0.49 microsecond. Okay, and the rise time is 0.01 microsecond, fall time is 0.01 microsecond. So this is going up to 2.2 volts. Okay, so now I can do a inverted wave, and that inverted wave will be the same thing. I'm going to copy, give it a DC value of 2.2. So this DC value is 2.2, and then this peak value is minus 2.2. Right, so now the wave is inverted. So I'm going to test this first, okay, before I do anything. Okay, and let's put a capacitance. We already have a capacitance inside as a feedback, so I'm just going to name this node as VO. Okay, so now I am going to also see what is the input, so I will call this as inverting input, and this one is a non-inverting input. Right, and then I need to add here the include file. Correct, and I need to do a transient simulation. So simulation transient. So go to simulation transient. Simulation transient, and I can specify what is the so let me change this. So this is 0.1 microsecond, sorry, and this is 0.1 microsecond, and this one is going to be 0.1 microsecond, 0.01 microsecond, and 0.01 microsecond. Okay, so I'm going to simulate for 2 microseconds, or let's say 4 microseconds, and the largest value of time step I'm going to put as 0.001 microsecond. Okay, so I'm going to hit simulate on this one. So in transient simulation, all you specify is the start stop time and the maximum time step. Okay, and you can hit simulate. Okay, first of all, I'm going to make sure that my inputs are correct. So this is one input, that's another input, so they are in quadrature, isn't it? Okay, and then I'm going to plot the output. Okay, so here I have a certain rise and fall, right? So I want to find out what is the slew rate. So to find out the slew rate, I have to put 2 markers. So I have a marker 1. So this should be at the 90% of the supply. So roughly it should be around 1.9 something. Then I want to put another marker at 10+% the supply. So that would be around 0.2 something, right? So that's done. Now I can find out the slew rate by writing an equation. So I can put here SR positive is equal to, so this is a positive signal, right? So SR positive is going to be equal to M1 minus M2. Okay, so you have to do M1 minus M2 divided by independent of M1 INDEP of M1 minus INDEP of M2. Correct? So that's going to be a slew rate positive. Okay, so let's just put it in a table. Go under equations and you have a slew rate formula available here. Okay, uh, so this is going to be volts per second, so I want to convert it into volts per microsecond, right? So I will just divide it by 1e6, so that's 1 microsecond. So this is going to be 392 volts per microsecond. Okay, so that's your slew rate. Up, a marker new, and then I'm going to put another marker, and somehow it's not exactly coming where I want to keep it, and another marker over here. Again, this is not coming where I want to keep it. Let's see on the other one. No, this is even worse. Okay, so slew rate negative. Okay, so slew rate negative is going to be m4 minus m3 divided by independent of m4 minus independent of m3. So this will be a negative number, right? So this will be slew rate negative. So go to equations, slew rate negative. So that's very large. Okay, now this is for driving a capacitive load, so I should have done a loading here. So if I go to lump components, let's load it with something like 1 picofarad. Sorry, let's load it with 1 picofarad. Let's see if this, so what happens to my slew rate. So that's fine. So let's run this again. Okay, so now I can look at the slew rate here. Kind of like these, I have to increase the time step. Again, slew rates are very good here, right? So I will be able to use this in as a comparator, or as a gain stage, or as a, in a feedback configuration, as a log amplifier, or inverting non-inverting amplifier, or a summing amplifier. So what we have done in this exercise, we did first the AC simulation, and we found out that, okay, the corner frequency, the gain, the corner frequency, the gain was 45.9, the corner frequency is going to be 3.6 megahertz, so it's usable with this high gain over here. It is even usable over here, but I would not recommend that. And then the zero crossing is at so with the compensation, the zero crossing is at 2.3 gigahertz, so unity gain bandwidth is 2.3, and at that zero crossing, the phase has rolled only by minus 102, so that means that there is 78 degrees of margin here, right? So this is the AC simulation, and then we looked at the transient simulation here, and we wanted to find out what is the slew rate. So that's the slew rate here. So I'm going to stop here for chapter 3 in ATS. Thanks a lot.